Hi, everyone. Welcome to today's webinar. We're joined by Jerry Liu, the CEO and co-founder of LlamaIndex, and Xander Song, a developer advocate here at Arize. We have a great workshop planned for today's session on how to power your LLMs on your proprietary data. Just a couple housekeeping items before we get started. So this session will be recorded and sent to you later today. And then also this is interactive, so please ask Jerry and Xander your questions in either the chat or the Q&A, which can be found at the bottom of your screen. And I will pass it off to Xander now for intros.
Right. Hey, everybody. Can you hear me? Awesome. So my name is Xander Song. I'm a developer advocate at Arize AI. Today, we are joined by Jerry Liu, the co-founder and CEO of LlamaIndex, and the title of today's workshop is Troubleshooting Search and Retrieval, Powering LLMs on Your Proprietary Data. Let's first go over the agenda of what we're going to talk about in today's workshop. Jerry, if you could hit the next slide for me. The first thing we're going to do is Jerry is going to give you an overview of LlamaIndex, and he's going to give you a demo of some of the capabilities of what you can use it for. We're then going to talk about the LLM deployment stack. And in particular, we're going to focus on search and retrieval. And we're really going to focus on what can go wrong with search and retrieval in production. And at the end of this presentation, you're actually going to get your hands on Arize Phoenix, which is our open source product for debugging and troubleshooting issues with production LLM applications. So without any further ado, I'm going to kick it over to Jerry, and he's going to give us an intro to LlamaIndex and a demo.
Awesome. Great. Thanks, Xander. It's great to be here and super excited for this workshop. As Xander said, I'll first give like a quick demo or overview of LlamaIndex itself, and then we'll talk about how we can actually properly evaluate, some of the applications that you can build within LlamaIndex with some of Arize's capabilities. So cool. To give a basic overview, LlamaIndex is a data framework for building your LLM applications. And the key thing that it unlocks is it gives you the tools to build LLM applications over your own private data, whether or not it's kind of like simple stuff like QA, chatbots, or even more advanced concepts like agents. And so, language models have a lot of inherent reasoning capabilities. A lot of application developers these days want to figure out how can they connect the power of language models with over their own private data sources, whether it's unstructured or structured data. And LlamaIndex provides both data management capabilities as well as query capabilities that you can just plug into your LLM application. And so diving into some of these components a bit more in depth, we offer some key components across the data lifecycle. So we offer data ingestion components to kind of load data from your sources and load it in a format that you can use in your downstream LLM application. Once you've actually loaded this data, you can then index this data with a set of data structures to actually store your data in a certain way to be used with your language model application. And we offer integrations with a variety of very popular storage mechanisms these days. Probably top of mind is vector databases. We also have integrations with, for instance, document stores and memory stores, those types of things. And the key idea is that we are able to kind of maintain the right state so you can build the LLM application over your data. Once you've actually defined the state, then you can actually define a retrieval and query interface in conjunction with the LLM to help you build your LLM application. So the high-level interface that this exposes is that by giving you the tools to build your own retrieval and query algorithms, then given any sort of input prompt, you can then do retrieval of relevant context from your knowledge corpus, and then you can use the LLM to then synthesize a knowledge augmented output. And so, we basically, if you've heard the term like retrieval augmented generation before, it's basically just a fancy way of saying like, how do you actually build LLM applications over your data? And so we offer a lot of the toolkit for retrieval augmented generation. And the thing is, we offer this both at a high level as well as at a lower level. So the high level API allows you to basically do all this stuff in about 4 lines of code. So you can easily have some sort of QA system. And I'll show that in a demo in just a bit. And if you want more customizability or flexibility, you can then go ahead and actually customize the individual modules. And then we'll talk about, once you actually get some initial prototype, how do you actually kind of iterate and understand if and when things are going wrong? And that's exactly where a lot of kind of Arize and Arize Phoenix comes in. This is just a very basic diagram that shows that if you want to build like any sort of like knowledge augmented LLM application, what LlamaIndex basically provides is the toolkit that wraps around your data as well as the foundation model, and then basically allows you to build some sort of interface where you could pass in any sort of rich query or task and then get back a knowledge augmented response. And then we provide you the tools to do all this stuff to wire together your data and the LLM to make this interface possible. This is a diagram showing what I roughly talked about in the first slide, which is kind of like the layers of abstraction that we have that allows you to define both state and also compute. So in terms of the actual abstractions over your data, we have your source documents, which are stored in some sort of, or your source documents can be fetched from any sort of like PDFs, APIs, workplace apps. And we have a site called LlamaHub, which offers over 100 different data loaders, which allows you to load in data from different sources into a format for your LLM app. Once your documents are loaded in memory, then you have data indices. And so, as I mentioned, like data indices help to provide a view of your raw data. And these indexes could include like embeddings, vectors, which we'll talk about in this workshop. They could include like they could include like keyword lookups. They could also include like text summaries. So once you've defined these indexes, you can then define abstractions like retrievers and query engines on top of your indexes. So a retriever is basically a module that helps to retrieve relevant documents given any sort of user query. A very basic example is from a vector database. A retriever could just be like doing top K embedding lookup from your knowledge corpus given some sort of query. And then a query engine is basically an abstraction that helps to manage retrieval and synthesis given a user query and gives you back a textual response. And the final result is that you're able to get back a response once you input something into this query engine, which in turn will call all these abstractions underneath the hood. So this is just to give you a short LlamaIndex walkthrough. And Xander has a way more in-depth walkthrough of how to use LlamaIndex over proper data sources. But this is just a basic example to showcase how things work. The first step is once we install the LlamaIndex package, I'm going to zoom in real quick. Then we have the OpenAI key, and then you have just some basic imports. The first step in a lot of these to build a retrieval augmented generation app is to load in some data. So this is just the basic example over our classic data set, which is Paul Graham's assay. We load in this data, store it in a text file. I'll just run this. And then we can load this in as a document. So this is using doing the first step, which is loading in data into some sort of document representation. And so if you look at the document itself, it's a very long text document. It contains a text field. Yeah, and basically this is just a big collection of text representing the stuff that you loaded from the essay. The next step is to actually index this document with a vector store index. And so this is the second stage where under the hood, we're actually taking this document, chunking it up using a text splitter, and then adding an embedding for each chunk. And by default, we're using the OpenAI embedding model. And then we're storing this in a memory store. The next step is, again, this is all like kind of a high level API because we're just trying to showcase how you can get started as easily as possible. And then underneath the hood, we have tutorials, and I think it's in this notebook too, how you can basically define in a more granular fashion the different components of your index and also the query engine. But in order to run a query against this index, let's say you just want to ask, like, what did the author do growing up? You query the query engine that's derived from the index, and it will basically do the steps I described, which is you'll do retrieval over the index and then do synthesis. And then this is the response that you get. And so I think that's basically it for the kind of initial demo. I think the very natural question that that kind of motivates the entire rest of this talk is basically like, okay, well, you set up this like RAG system, and I can ask questions of your data in like 3 or 4 lines of code. How do you actually properly, like understand it a bit better and understand when things are going wrong and why, right? And so I think the part of the motivation here is how can you actually understand like whether or not the kind of like questions you're asking and the responses you're getting are correct, and whether or not data starts to become a little bit out of distribution. And so without further ado, I'll pass it over to Xander.
Thanks, Jerry. Looks like you're getting a lot of questions in the chat too, so I would take a look there. Awesome. I'm going to go ahead and share my screen and pick up from where Jerry left off. Let's see. All right, are folks able to see my screen? Right, I'm seeing nods, I think. Awesome, thumbs up, awesome. All right, here we go. So Jerry already touched on this, but I wanna just keep it really high level for just a moment, and let's talk about like, why do I need search and retrieval in the first place? And to illustrate this point, let's actually consider an example. Imagine that you go to ChatGPT and you ask ChatGPT, tell me about Arize. If you ask ChatGPT, tell me about Arize, the answer that you're going to get is, I'm sorry, as of my knowledge cutoff in September 2021, I don't have information on Arize. So the TLDR here is that, Arize is a little bit too new, wasn't included in the training set for ChatGPT. But if you were to actually copy paste the homepage of our documentation, paste it into the ChatGPT interface, and then ask ChatGPT, tell me about Arize, you would get this answer. Arize AI is a real-time machine learning, ML observability, and explainability platform. So you get this nice answer. So what is this illustrating? Search and retrieval enables you to provide your own context and your own data when you're building an LLM application. And you might need to do that for any number of reasons. It might be that the data that you're trying to actually provide a question answering service for is proprietary, or it might be that it's just too new to have been included in the training set for one of these large language models. The second reason is that you actually are able to ground the response from the LLM in a trusted source of information. In this case, a piece of documentation that was written by a human being. And the third reason is that search and retrieval provides this really easy way to actually update the behavior of your LLM application by swapping in and out documents from your knowledge base. Okay, so hopefully that's clear, like at a high level, why are we talking about search and retrieval? And Jerry already touched on this, but I'll just touch on it really briefly. Like, how does search and retrieval actually work? Like, what's going on under the hood? With search and retrieval applications, you start out with some kind of knowledge base. And the knowledge base that we're going to be talking about today is the Arize documentation. So you start out with some kind of knowledge base. And one of the cool things that LlamaIndex provides you with is the ability to actually chunk your documentation, chunk your set of documents, and compute embeddings for each of those chunks. So that's what you're seeing here. Different chunks of the Arize documentation and the embeddings corresponding to those chunks, and then to store them in some kind of vector store, whether that is an in-memory vector database like Chroma, or like a Pinecone, a Milvus, etc. And at actual query time, what happens is one of your users is going to send some kind of question to your question answering service. An example would be like, how much does Arize cost? The question is going to get embedded. And then we're going to do this retrieval step where we're actually going to use the cosine similarity. So compare the cosine similarity from this query embedding with each of the embeddings in our knowledge base in order to get the most similar chunk of documentation. And then we're just going to take that chunk and format a prompt. And the prompt might look something like, the user is asking this question, how much does Arize cost? Here's some relevant context that we retrieved from the vector database. Now here, GPT-4, can you now give me an answer given this additional context? So that's at a high level how these applications work. Now let's talk a little bit about what can go wrong, right? The way that these applications are typically deployed, right? You have a user query and you have some kind of service that's a question answering service. And even before you add in this search and retrieval step, there are a couple of things that can go wrong. The first thing that can go wrong is LLMs, like, LLMs from any foundation model provider, they can hallucinate, they can make up information, right? And the second challenge is that sometimes evaluating the output from an LLM is actually quite difficult. Maybe you get some user feedback, right? A thumbs up or thumbs down, but actually interpreting that user feedback can be quite difficult. Is the user actually complaining about a legitimately bad response, or is it just based on user preference, like they don't like what you're saying? User feedback can be a very sparse signal. So there's problems with just relying purely on user feedback. And then the picture only becomes more complicated when we actually introduce the search and retrieval step. Now we're, again, embedding the query, retrieving relevant documents, enriching the prompt before we send it off to that foundation model provider. And this introduces another failure mode, namely the failure mode of bad retrievals. What if I retrieve the wrong piece of context from my knowledge base? Or what if the user is actually asking a question that my knowledge base doesn't have an answer to, right? So those would be what I would consider to be bad retrievals. And where Arize comes into the picture is we are providing you with a foundational layer of LLM observability in order to help you, first of all, detect these issues when they arise in production, and then pinpoint the root cause of the issue. And in today's workshop, we're going to be focused in particular on this section of the LLM deployment stack. And we're going to be focusing on how can I detect when my LLM application, my search and retrieval application, does a bad retrieval, doesn't get the right piece of context. So this is going to be the focus of the workshop. And to just dive into that red box a little bit more, there's a couple of different ways that search and retrieval can go wrong, right? We already talked about steps 1, 2, a chunking of the documentation, the user asks a question and it gets embedded. The first thing that can go wrong in the search and retrieval step is you might not have any similar documents, right? So someone might ask a question and there might not be an answer in your knowledge base, right? And then the second thing that could go wrong is even if there is something that is similar, as in it's on topic, right? Sometimes being similar in the sense of having a high cosine similarity is not enough. Sometimes that doesn't ensure that the document that you actually retrieve from your knowledge base is actually relevant to the question that's being asked. And if that seems really abstract right now, hopefully it becomes very concrete in just a moment. Cool. So now we're actually going to get into the interactive portion of the workshop. But before we do that, I want to highlight a few things. We're going to be using Phoenix, which is our open source project from Arize. A few things I want you to know about Phoenix is you can just pip install it in your notebook environment. It's an application that actually runs alongside your notebook. So if you're running your notebook on your laptop, Phoenix will run on your laptop. If you're running your notebook on Colab, you can run Phoenix on your Colab server. So it runs alongside your notebook in your notebook environment. And the third thing that I want you to know about Phoenix is that Phoenix helps you detect issues and find the root cause of issues. That's our model. That's our MO. And what kind of issues are we talking about today? Well, today we're going to be focusing in particular on issues with search and retrieval applications. So go ahead and open up this notebook link. I'll go ahead and do that too. So here's the notebook that we're going to be running today. Before we actually dive into that too much though, I want to give you a sneak preview of where we're actually heading. So I've already pulled up Phoenix. This is the example that we're going to run in the notebook together. And what you're seeing here is actually a low-dimensional representation of our query data, of our queries in blue, and our knowledge base entries, our chunked documentation in gray. And if you just look right here, you'll notice that there are a couple of queries that are kind of out here in left field. And it turns out the story I'm going to tell you is that this cluster of queries that's out here in left field is all the way out here because it's actually questions around the price of the Arize platform. And it turns out that we don't have any information about price in our documentation. So you're actually seeing that in the low dimensional representation of these embeddings, you're seeing that the retrievals to actually grab the context for each retrieval augmented generation, it's having to go pretty far away. It's having to basically jump out of the cluster to a different portion of the embedding space in order to actually grab that piece of context. And it turns out that all of these pieces of context that we're grabbing in this example are actually irrelevant because they're actually kind of out in left field. So this is the TLDR. This is just to kind of tease where we're going to be going. I'm going to pause right there and just see if there's any questions in the chat before I move on. I'm seeing a lot of comments, but I want to make sure that we're kind of clear on direction before we hop into the details. Super cool. All right. What is the low dimensional representation? Yeah, thank you, Tatiana. That's a great question. The low dimensional representation is we're going to be actually taking the embeddings. So you remember we're embedding each user query at query time, and we've also embedded each chunk of documentation when you create your index with LlamaIndex. So we have those embeddings. What we do is we take those high dimensional embeddings, which in the case of text embedding ADA2 from OpenAI are going to be like about 1500 dimensional. We take those high dimensional embeddings and we're going to reduce the dimension of those embeddings. And that is what you're seeing. That's what you're seeing here is this 3-dimensional reduced dimensional representation of your embeddings. Cool. See. Oh, okay. So another question is it open source? Yes, Phoenix is fully open source. You can pip install it in your notebook. And that's actually what you're going to be doing today during the workshop. So fully open source, the code is on GitHub. And maybe one more question. Looks like Luke W has a question around, okay, a couple of these are pretty specific questions. We're gonna come back to those at the end. All right. Awesome. So let's go ahead and actually dive into the interactive portion of the workshop. So Maggie, I think, has shared out the link to the notebook. Once again, the link to the notebook is just bit.ly llama-index-phoenix-tutorial. Okay. The first step is if you have an OpenAI key, let's go ahead and grab that key. So I do have a key. I'm going to grab my OpenAI API key, copy, paste, and I'm going to paste it into step 2 down here where it says OpenAI API key. I'm going to paste it right here. And then I'm going to go ahead and hit run all on my notebook. Now, if you don't have an OpenAI API key, don't worry, you'll still be able to run this notebook. What you're going to need to do is selectively run cells. Any cell that has one of these thought bubble emojis in front of it, you need to skip. Those are the cells in the notebook that are going to require an OpenAI API key. But if you skip those cells, you'll still be able to use Phoenix at the end of the notebook. You just won't be able to actually use the chatbot interactively. Cool. So that's going to take a minute. We're going to go ahead and let that run for just a moment. And while that's running, I want to give you a high-level overview of the chatbot that we're building. So here's the actual specific architecture for the specific implementation of the chatbot that we're dealing with. I'm going to walk you through the architecture in 5 steps. Step 1, the user is going to send a query. And the first thing that we're going to do is your LlamaIndex chatbot, which we're going to, I'm going to show you the code for it in just a moment, but your LlamaIndex chatbot is going to embed that user query using OpenAI embeddings. So it's going to actually make a request to the embeddings API for OpenAI, in particular to the text embedding ADA2 model, in order to get an embedding back for your user query. Okay, so now we've got the embedding. In step 3, we're actually going to retrieve the relevant documents from our knowledge base. And what does that mean? It just means that we do a similarity search, in this case by cosine similarity, over all of those embedded pieces of context in our knowledge base. And again, the knowledge base in this case is the Arize documentation. And in this case, this particular chatbot is configured to retrieve 2 pieces of context, the 2 chunks of documentation that are most similar to the query by cosine similarity. And we take both the query and the context, and we then format a prompt. And what that prompt looks like in this case, it actually looks like just like this. This is the exact prompt template that we're actually using. This is the default text question answering prompt template in LlamaIndex. It goes like this. It says context information is below, and then it pastes in those two pieces of context that were retrieved. And then it says, given the context information and not prior knowledge, answer the question. And then it pastes in the user's question. So nothing fancy. It's just literally formatting the context and the query into one prompt, which it then sends to the chat completions API for OpenAI. In this case, we're using GPT 3.5 Turbo, but you can use whatever chat completions model you want in order to get a response. And that response is the one that we're sending to the user. So let me show you what this actually looks like in the notebook. Again, one of the really great things about LlamaIndex is that it lets you define this relatively complicated chatbot architecture in a couple of lines of code. And where is that happening? I think I maybe skipped it. Where did it go? Yeah, it's actually just right here. It's these lines of code that are actually just defining this architecture that I showed you right here. So it's a couple of lines of code, boom, you've got your chatbot architecture. Awesome. So next step that I want to talk about is I want to talk about what does the data look like? If you want to use Phoenix, what do you need your data to look like? And actually the notebook is actually the whole point of the notebook is just getting the data into this format, basically. So we won't go through all the details in the notebook, but the TLDR is we're trying to get the data to look like this. We've got two data frames, one data frame for our knowledge base and one data frame for our query data. The knowledge-based data frame is going to have a couple of pieces of information. It will have the actual documents itself. So here is one of our chunks of our documentation. It says to get started quickly, you can use the scripts provided with the distribution, extract the tar file, yada, yada, yada. And then here's the actual embedding corresponding to that chunk of documentation you can see right here. So that's really all we need for the knowledge base. And for the query data, we're actually going to need a few additional pieces of information. We've got the query itself. So one example query could be, how do I use your SDK to upload a ranking model? That's a question someone might ask about Arize. Here's the embedding. So again, the first step in our chatbot is we take that query and we send it to the embeddings API from OpenAI, and we get this embedding for the query. We've also got a few additional pieces of information, though. We've got the first retrieved piece of context. So in this case, this is a chunk of documentation. It says ranking models are used by search engines, et cetera, et cetera. Here's the cosine similarity for that particular retrieval. And here is the response generated by the chatbot. So the response back to the user was, to use the SDK to upload a ranking model, you will need to first install the SDK, et cetera, et cetera. We've got a couple of additional fields. We've got the user feedback, which is just a thumbs up or a thumbs down signal, +1 for thumbs up, -1 for thumbs down. This would just be, imagine on your chat interface, you've got a thumbs up or a thumbs down signal, a button that your users can press. And these last two pieces of information, we're going to talk about in just a minute. Awesome. And another cool feature here that I wanted to tease is we've been actually working on tighter integrations with LlamaIndex. In particular, we just released what is called an open inference callback handler. This is part of the LlamaIndex library. It should be part of the next release. And what this is doing is it's a callback which you can attach to your LlamaIndex application, and it's actually going to store off all of the data that you need to get into Phoenix and into Arize easily. So this is just streamlining the process of saving off data from your chat application so that you can then go and debug it in production. And another thing that I'll tease is that we've actually also got some examples of using this for logging. So logging to file, logging to cloud storage. So you can use this for logging purposes in production, in addition to using it as a store, a data frame store in your experimentation workflow. Cool. So I think now I would like to actually jump into the application itself. Let's go ahead and scroll down to the bottom of the notebook. And you can see right here at the bottom of the notebook, we've got this phoenix.launch app call. And this is actually going to launch Phoenix. Again, it's going to be running on your actual Colab server, but you're able to open it up right here in your browser. And the first thing that I'm going to do is I'm going to click on my embeddings, my prompt embedding right here. This is going to take me to that page that I showed you just a few minutes ago. And here you go. Once again, what you're looking at are your query embeddings in blue, your database entries in gray, and let's go ahead and close the time series. And once again, I'm going to tell you a couple stories about like how can you automatically surface up problem areas in your queries, like what kind of queries or is your chatbot struggling on. So let's go ahead and start down that path, right? The first problem I want to address is like, how can I detect bad responses, right? And what do I mean by bad responses? In this case, I just mean responses that my end user has flagged as being problematic, thumbs down responses. How can I see those responses in the application? So let's go ahead and do that. So the first thing that you can do is you can actually color your data, not by the data set that it belongs to, not by query versus corpus data, but you can color by what we're calling a dimension. A dimension is just, think of it as a field of your data. And the dimension that I care about right now is user feedback. So now you can see the color of all of the points in my point cloud have changed. So now I'm seeing the coloring based on user feedback. So purple means thumbs down, green means thumbs up, and the gray points are either corpus data points, like, corpus data points don't have a thumbs up or a thumbs down. They're either corpus data points or they are, what do I want to say? Query data points for which the user did not give a thumbs up or thumbs down, right? So here you go, you can actually see exactly where your users are giving thumbs up or thumbs down. But not only that, let's go up here to this metric dropdown. This is really where the cool part begins, is we're able to sort by the average user feedback on a per cluster basis. So now I'm going to point your attention to the clustering section over here. What we've done is we've actually taken your embeddings, we've reduced the dimension, and then we've clustered them. And you can actually sort, if you select lowest metric value, now we're sorting the clusters in order to, in ascending order in this case, in order to bubble up those clusters that have a low average user feedback. So let's actually see what this looks like. It looks like this is the cluster with the lowest average user feedback. And if I actually look at the points in this cluster, you will notice a theme. This is that pricing cluster that I mentioned just a minute ago. So the first question is, what is the cost of the Arize platform? And it turns out that for a lot of these questions, there's actually no valid context in our knowledge base, again, because our documentation doesn't contain information about pricing. So the users in this case are actually complaining like, hey, I'm getting weird responses or bad responses that are incorrect. So here's an actual example of a pretty bad response. The question is, do you have a pricing calculator? Wait, no, this isn't the one I wanted. Where's the one I wanted? Here we go. This is the one I wanted. Yeah, this one is actually a really good example. The question is there a cost for Arize beyond an annual subscription price? And the response from the chatbot is yes, there may be additional costs for Arize beyond an annual subscription price. And it turns out that this is actually a hallucination. The chatbot in this case is actually completely making up this answer. You can actually see right here the two pieces of retrieved context. Here are the chunks of our documentation that were retrieved. And if you read through these chunks of documentation, it actually mentions nothing about cost and nothing about subscription pricing. And it turns out Arize doesn't actually have any subscription plan. So this is a completely made up answer by the chatbot. And you can imagine this is actually pretty problematic because it's making up an answer to a question that is fairly sensitive. You can imagine that this is actually could be something that would, damage a relationship with a customer potentially. So this is the kind of danger that Phoenix is meant to guard against. Okay, so hopefully now I've shown you how you can bubble up problematic areas based on user feedback. And user feedback is actually a really great signal. We highly encourage that people use it. It's great because it's directly measuring the thing that you care about the most, which is end user experience, right? But that being said, it does have a couple of cons. The first con that I would mention is it does actually require that your users hit that thumbs up or thumbs down button. You actually need a signal from your users, and you may or may not have that signal for every kind of application. Or even if you do have that thumbs up, thumbs down button, it may be a sparse signal. Maybe your users are just not actually hitting that button very much, right? And the second drawback with this particular metric is it's actually not going to help you pinpoint the exact mode of failure. All you know is that a user said, hey, I like the response, or hey, I don't like the response. You don't know where in this complex chatbot architecture something has gone wrong to lead to that undesirable outcome. Okay, so the next story I'm going to tell you is, let's suppose that we don't have user feedback. We don't have that signal from the user. Would I still be able to figure out what kinds of clusters or what kinds of queries my users are asking that are maybe missing from my knowledge base? And I've kind of already teased this idea a little bit by showing you that cluster of pricing questions that was kind of out in left field. But let's see how Phoenix can actually help you surface this cluster automatically. So I'm going to come back to the color by dropdown here. I'm going to select data set. So now, once again, my data is being colored by queries in blue, documentation in gray. And I'm going to go up to the metric dropdown again and select query distance, and go to the sort dropdown and select highest metric value. So in this case, my clusters over here in the left sidebar are being sorted based on this metric %query. So the clusters at the top are going to be those clusters that are pure query data, right? And why is it a problem? Again, why is it a problem if your clusters are like 100% query data? It just means that there's no nearby documentation in your knowledge base from which that question could try to actually draw an answer. You can see, again, this first cluster that we're surfacing up, which is the pricing cluster, it's all the way out here in left field, far away from your knowledge base entries. So this is the situation where we're actually able to show you those areas of user interest, like what kinds of questions are my users asking that aren't answered by my documentation. And importantly, we're able to do this even in the absence of any feedback signal from the end user. Yeah, and so just to drill this point home, again, the top cluster here that's being automatically surfaced, it's that very same pricing cluster, the same questions about the pricing of Arize that we don't have any answers for in our documentation. And so you can imagine, like, once you reach this point, maybe your actionable next step is to actually identify those topics that people are interested in, and now you can go and actually augment your knowledge base, but doing it in a way that's based on the actual user behavior, based on the actual interests of your end user, right? So that's the value add here. Cool. So we've gone over when you might use query percentage as the metric to surface up problematic clusters. But query percentage has one downside. And the downside of it is that, again, it's identifying broad topics that are missing from your knowledge base, but it's not necessarily going to identify small gaps in your knowledge base. And what do I mean by a small gap? I mean, a lot of the time, your users might be asking questions on a topic that is well documented in your knowledge base, but the particular answer might not be answered. It could be like they're asking questions about your SDK, and there's lots of documentation about your SDK, but this specific question about the SDK is not being answered. So how can we actually get a more granular metric that is going to surface up individual queries that are not being answered? That's the next task that we want to think about. And the first metric that you might think about for trying to do this would be something like cosine similarity, right? You might think, oh, well, we used the cosine similarity to actually retrieve those documents from our knowledge base. Maybe we should expect that having a higher cosine similarity means that that is an actually relevant piece of documentation, and having a low cosine similarity means it's not relevant. And we should expect that those queries that have that high cosine similarity are probably more accurate because they got better context. They got better chunks of documentation during the retrieval step. So that's an expectation that you might have initially. And I think the story, it turns out, as you're going to see in just a moment, is maybe a little more complicated than that. But let's actually take a look at this particular metric. So once again, in the color by dropdown, I'm going to select the dimension field. And then in the dimension dropdown, I'm going to select document similarity 0. What this is the cosine similarity to the first retrieved document that is the most similar document by cosine similarity in your knowledge base. And you can see here in the legend, the cosine similarity, it runs the gamut between about 0.74 all the way up to about 0.9. The darker colors being lower cosine similarity and the brighter colors being higher cosine similarity. So let's actually deselect all of the points for a moment. I just did that by clicking right here on the dimensions button or the dimensions checkbox. And I'm going to just select the lowest cosine similarity points now. So it's a little tough to see, but there's actually a couple of purple data points on my screen. And I'm going to go ahead and use the lasso right here. And I'm going to draw a wide lasso and just select a lot of those data points. And let's actually take a look at some of these queries that have a low cosine similarity with the knowledge base. Maybe I want to look at this one right here. What counts against my planned usage? So that's the question. And here you can see that the document similarity 0 and document similarity 1, so those are the cosine similarities to the two pieces of retrieved context, those are quite low values for cosine similarity. You can see it's near the bottom of the spectrum for cosine similarity in this distribution. And as you might expect, it turns out that both of these retrieved documents in this case are not relevant. So again, the question is, what counts against my planned usage? The first document is talking about ranking, totally irrelevant. The second one is talking about monitor settings, again, totally irrelevant. So this is a case where the cosine similarity is acting as a pretty good proxy for the relevance of the document. Let's go ahead and look at another example here. I'm going to deselect the purple checkbox here, and I'm going to select the green checkbox. So now the points that I'm seeing in my point cloud are only those points that have the highest cosine similarity with their retrieved documents. Let's take a look at those query points. Okay, and let's go ahead and look at this point in particular. The question is, again, what drift metrics are supported in Arize? And the response is Arize supports drift metrics such as population stability index, KL divergence, and Wasserstein distance. Okay, if we look at the document similarities, they are 0.87. So that's a high cosine similarity right near the top of the range. And if you actually read through these documents, what you'll notice is that one of the documents is relevant. So I think this is the relevant one right here. Arize calculates drift metrics such as population stability index, KL divergence, and Wasserstein distance. Okay, so that's very relevant to the question. And that is actually the very piece of context that the chatbot is drawing from when it answers the question. So that's what we expect, right? We have this high cosine similarity, a relevant document, but there's a little bit of a complication because right here, we also have basically the same cosine similarity. We have another document here, and this one is talking about the same topic. It's talking about drift. It's talking about metrics. So drift monitors measure distribution drift, which is the difference between two statistical distributions. But the thing is, it's not really answering the question. The question was, what drift metrics are supported in Arize? This piece of documentation is talking about the same topic, but it's not actually relevant to the question. And this is where you might start to suspect that, hey, maybe cosine similarity isn't really doing such a good job at acting as a proxy for relevance. And what we really care about is relevance, after all. We want to get relevant documents for our queries. So I think the example that really drives this home is, again, that same pricing cluster that we've been looking at. Let me go ahead and select those points. So this is, once again, that same pricing cluster. And again, all of these questions don't have relevant context in our knowledge base because we don't have any information about pricing. So, all of these are irrelevant retrievals But what you're seeing is actually the cosine similarity really runs the gamut. You've got some cosine similarities, some retrievals with low cosine similarity. You've got some retrievals with high cosine similarity. And if you actually look at some of these examples, you start to get a feel for why. So here's the question. What is the cost of the Arize platform, right? Here's the question. And here's the first piece of retrieved context. Arize is an open platform that works with your machine learning infrastructure. And it turns out, again, this piece of retrieved documentation is not answering the question. It doesn't have any information about cost, but it has a high cosine similarity with the question because it bears these superficial similarities to the question. In particular, it's also talking about Arize. It's also talking about platform. So it's got these superficial similarities with the original question that cause it to have a high cosine similarity, even though it's not a relevant document for your retrieval. It's not answering the question. Okay, so hopefully at this point, I've convinced you that similarity is not the same thing as relevance. Just because you have a high cosine similarity doesn't mean that you're going to be answering the question, right? That's what I've been trying to convince you of. As the last thing that we want to show, the last thing I want to show is an idea that we've been playing around with to actually address this problem more directly. And the idea is using ranking metrics, and in particular, LLM-assisted ranking metrics, in order to directly measure the effectiveness of that retrieval step. So what does this look like? I'll run you through a quick example. The idea is that we're going to take each query and each retrieved piece of context, and we're going to ask GPT-4, does the context answer the query? And GPT-4 is going to say, yes, it answers the query, it's relevant, or it's going to say, no, it doesn't answer the query, it's irrelevant. And then we're going to have this actual relevance signal from which we can compute a ranking metric. So let me walk you through a concrete example. Here's a query that you might ask of the Arize documentation. The query is, what format should the prediction timestamp be? And here's the first piece of retrieved context. The first piece of retrieved context says, the timestamp indicates when the data will show up in the UI, sent as an integer representing the Unix timestamp in seconds. So there's the answer right there, the Unix timestamp in seconds. And in this particular case, GPT-4 correctly classifies this particular piece of context as being relevant to the query. Now, here's another piece of context that was also retrieved for this particular query. The query is, the context says, the prediction timestamp represents when your model's prediction was made, time of inference. It's a timestamp column, and it goes on. But the point is, it's talking about timestamps, but it's not talking about the format of timestamps. So it's actually not answering the question. And ChatGPT or GPT-4 correctly says that this is an irrelevant piece of context that's not addressing the question. So once we go through and we get for each query context pair the relevant or not relevant classification from GPT-4, we're actually able to compute an LLM-assisted ranking metric. And the ranking metric that we care about right now is precision at 2. What is precision at 2? It is just the proportion of the retrieved documents that are relevant according to GPT-4. So if you have a precision at 2 of 0, that means that 0 of your 2 retrieved documents were relevant. If you have a precision at 2 of 1/2, that means 1 of your 2 retrieved documents were relevant. And if you have a precision at 2 of 1, that means all of your retrieved documents were relevant. And again, why do we care about precision at 2? If you have a 0 precision at 2, it means you're not doing a good job at that retrieval step, and your chatbot's not very likely to have an answer. Whereas if you have a high precision at 2, if you have a non-zero precision at 2, you've at least got 1 relevant piece of context and potentially more to work with. So your chatbot is more likely to give you a good answer. So let's actually jump in to Phoenix once again, and let's just see what this looks like. So once again, I'm going to come to the color by dropdown. I'm going to select as the dimension the OpenAI precision at 2. And what you're seeing here is now my data is being colored by precision at 2. You've got your purple data points, which represent 0 precision at 2. You've got your blue data points, of which there are a couple right here, for example, which represent where your precision at 2 was 1/2, meaning 1 of the 2 retrieved documents was relevant. And you've got your green data points here, meaning that all of the retrieved pieces of context were relevant to the query. And we can once again sort our clusters by average OpenAI precision at 2. And let me just make sure that I'm sorting in ascending order. So lowest metric value means I'm sorting those clusters in ascending order with the lowest precision at 2 clusters surfaced first. And once again, let me just rotate this thing around. Once again, what I expect to see is that, again, the first cluster that we're surfacing as problematic is the same pricing cluster, which again is all purple. All purple, meaning that GPT-4 in this case has actually looked at all of the queries and the retrieved pieces of context, and it's saying, hey, this is a problematic cluster because all of these queries had failed retrievals. And so all of the responses from the chatbot are either likely to hallucinate or just not going to have useful information for the end user. So that about wraps it up in terms of what I wanted to cover for today. Looks like we're running right on time, so we'll have a couple of minutes at the end for questions. In terms of shout outs, I want to say, first of all, thanks to Jerry. If you haven't tried LlamaIndex already, give it a go. It's really easy to get started with, just a couple of lines of code. If you enjoyed the presentation, check out Phoenix on GitHub. We'd love it if you'd leave us a star. It really helps us build momentum on the project. If you have any questions, any product feedback, or if you run into any issues while you're using while you're using Phoenix, go ahead and join the Arize AI Slack community and send us a message in the Phoenix support channel. We're very responsive in that channel. And if you want to talk to me personally, you're always welcome to email me directly at xsong@arize.com. And with that, I'm going to stop the presentation and we will go ahead and answer some questions, of which it looks like there are quite a few in the chat.
Yeah, and also just chiming in, like, huge props to Xander for putting together this amazing workshop. Honestly, a lot of this is just very in-depth and thorough on the different types of metrics that you can use to evaluate and help correct bad retrieval. And so if you guys haven't checked out this notebook, please do. And as Xander said, we'll land the kind of callback handler stuff very soon. And so in the next release, you'll see the Arize, the integration with Arize from LlamaIndex. Maybe one question, Xander, I'm just pulling this from the chat, is I think earlier on, does Arize use like TSNE or UMAP for a lower dimensional representation, and how does that integrate with like maybe like cross encoders like Cohere or Rerank? Curious if you have thoughts on that.
That's an interesting question. Okay, so the question is around, like, first of all, what dimensionality reduction technique are we using? And the second is how does that play with cross encoders? Yeah, so for the first question, we're using UMAP, as you said. We're using UMAP just because in practice, we found that for this particular application, that's the one that plays best with the clustering algorithm that we're using, which is HDV scan. In terms of like how it plays with cross encoders, I'm actually not sure of that. I don't think that we've played around with that yet, but I would really love to actually experiment with that and get a better idea. Yeah.
Okay, no worries. I'm just digging through. I think there's stuff in both the webinar chat and then also the Q&A session. Nice. What happens if so like maybe this is a question about like LLM based eval, but like what happens when GPT-4's assessment of the relevancy metric is erroneous, and is there ways to kind of get around that?
Yeah, that's such a good question, and I think this is something that we're actively thinking about. So the question is like, okay, we're in this brave new world where we're using LLMs to evaluate the output of other LLMs, and can't that get problematic if there's no human in the loop? Maybe that's the concern, right? And I think GPT-4 is capable of making mistakes. The prompt template that we have for evaluations in the notebook is not perfect, and I think we know that we need to iterate on it. I think probably long-term, the answer for this is probably to keep a human in the loop in some capacity to kind of gut check some of the relevance classifications from GPT-4. But in general, we've actually seen pretty strong, we've seen like GPT-4 doing a pretty good job of doing these relevance classifications. We also tried other foundation models like the text bison model from Vertex AI. And we found that by and large, GPT-4 and Vertex AI, they agree on these relevant classifications the vast majority of the time, something like 97, 98% of the time. So I do think the idea of LLMs evaluating other LLMs is something that's gaining traction in the community. But I think it's a good question. Is like, what does it look like? Are we investing? How much do we trust it, right? And I think that's still something that we have to build trust in and potentially keep a human in the loop, even in the long run.
Great. I just realized there's this like answer live button that you click on the QA, so I'm going to try this.
Oh, nice.
Are you seeing that? Like, I think, yeah, basically like in terms of what's being clustered, is it the source documents, chunked and embedded, or the logged user interactions?
Oh, okay. Yeah, good question. What's being embedded? Is it the source documents or is it just the queries? I think that's the question, right? Which data points are being embedded? So to go back to Phoenix, the thing that is getting embedded is both the source documents in gray and the user queries in purple. And maybe I should have actually just shown you a couple of these data points to make it a little bit more concrete. Let me just circle a few of these right here, just so that it's really clear. So here in blue, you can see, this is actually a really great example. Here in blue, you can see a couple of prompt response pairs. So again, the prompt here is the question from the end user. The response is the response sent back from the chatbot back to your end user. And this question says, can I copy a dashboard to a new space? The chatbot responds, yes, you can copy a dashboard to a new space. Here's another question about a dashboard. And then the gray data points are the actual chunks of documentation. So here's a chunk of documentation. It's got some kind of formatting in it. But here's the important part, create a dashboard in a space for viewing model data. So what you're seeing is that similar queries are getting embedded nearby similar pieces of documentation in the embedding space. That's what that's meant to illustrate. So yeah, TLDR, both the queries and the documentation chunks are embedded in the same space.
I think, yeah, I'm happy to let you guys take lead on the timing for this, but I know one pretty important question, maybe this could be the last question, is just like, I've seen this like across like 3 different comments, is like, after all this like visualization and detection, what are kind of like the action items? Like, how do you actually find solutions to bad retrieval?
Yeah, that's such a good question, right? Like, we get you to the insight, like, what do I do next, right? And I think in general, like these systems are quite complex, right? And there's no one size fits all solution. So let me just go back to this table right here. I think our goal as a product, Phoenix's goal as a product, is to get you to that actionable insight. And the exact action you take is going to depend on what's going on, what is the mode of failure, right? So for example, if you identify that there's some area of your documentation or some area of user queries that are just far away from your knowledge base, the actionable next step would be to enrich your knowledge base, answer those questions that your users care about that you don't currently have answers to in your documentation, right? That could be one actionable next step. In terms of other ideas, right? Like, I think the question is really around like, okay, I see that maybe my retrievals are failing. How can I fix that situation? And I think that's really where we're driving the product, is we're going to be providing you with more experimentation workflows and more opinionated workflows to help you, to not only help you get to the insight around what the issue is that's causing the issue, but also help push you in the right direction for actually taking an actionable next step.
Yeah, and I think from the LlamaIndex side, I think in terms of solutions, like, assuming we're operating under the framework of like kind of top K retrieval, there's different things that you can do. So one is to try out like different kind of embedding models. There's kind of like bi-encoding, which we all do with like OpenAI APIs. You could try like fancier stuff, which, would probably need to work with Arize on like integration, but like kind of cross-encoding, like fancier encoding models, which like encode both the query and the context. And then the other part is like, beyond like kind of just pure embedding lookup, there's additional things that you can do beyond that to kind of improve the relevance of the context of the query with respect to like, you can do re-ranking, you can use the LLM itself as like a second stage pass. And so there's kind of like both the core like embedding based models, but then stuff you can do outside of that to really like help increase retrieval relevance. Because then the end, that's like what's the most important.
Yeah, yeah. And where we're trying to get to as a product is we're going to help you help you assess A/B test different model versions, right? Different chatbot versions, and say, oh, for this set of queries, I can see that my retrieval relevance has actually improved by using this new chatbot architecture, right? So that's where we're driving as a product too. Yeah. Well, awesome. It looks like there's still quite a few questions in the chat. I'm happy to stick around. Jerry, do you have a few minutes or?
I might have to hop off, but
okay.
Yeah.
No worries. Well, but okay, I'm going to stick around. Everybody, please just give a big thanks, big round of applause for Jerry. Yeah, thanks so much to Jerry and LlamaIndex for making this happen. We really appreciate the opportunity. Really appreciate the collaboration. And yeah, thanks, Jerry. We'll see you next time.
Yeah, no, it was great being here, and thanks so much, Xander, for helping organize this. And take care, guys. Bye.
Awesome.